Well, it's a great pleasure to be speaking this afternoon in this session on resilience. Joe De Silva has very eloquently described the importance of thinking about disaster and engineering our infrastructure in the context of potential disasters. I'm going to address this afternoon some new engineering aspects of resilience in the context of our physical infrastructure. And I will briefly describe some of the work I and my colleagues at Cambridge are doing on the subject of engineering resilient infrastructure. This is very much part of a large project funded by the EPSRC and the Technology Strategy Board. So there really is no question that whether one's talking about a developing country or a developed country, that high-quality national infrastructure is absolutely essential for supporting economic growth, productivity, attracting globally mobile businesses, and, of course, for promoting social well-being. And modern construction and infrastructure needs to be optimized in terms of efficiency, in terms of cost, low carbon footprint, and service quality. And, of course, very much the focus of this session this afternoon, it needs to be resilient and robust and adaptable to changing patterns. And by those changing patterns, we, of course, primarily think about climate change and natural hazards. It needs to be innovative, of course, across all sectors, driven by business in partnership with governments. So what I'm going to be talking about is some of the newest thinking as to how our construction industry and how infrastructure can be changed in quite radical ways. Firstly, we've heard quite a lot already from Joe about the vulnerability of our infrastructure. And there are just 4 examples here. There, of course, are hundreds more. But I want to focus on these just to illustrate some important points. The one on the top left and the one on the bottom right are examples which we're all familiar with of our existing infrastructure actually being a lot more vulnerable than we realize as engineers and as operators. So whether it be a bridge collapse in Minnesota, which was very tragic, resulting in loss of life, or whether it be a high-pressure water main bursting with enormous cost implications, we have a lot of infrastructure in our urban environments which are extremely vulnerable, and we may not realize it. The example on the top right is an example of vulnerability during construction. This was a station for a new metro being constructed in Singapore, which collapsed without much warning and resulted in loss of life and enormous cost, running into many tens of millions of dollars. And the one on the bottom left, of course, is another example of what Joe was showing earlier of vulnerability to flooding. And this was a photograph taken of an electricity substation in this country in 2007 as a result of really rapid and unexpected levels of flooding. Now, The Economist magazine got interested in this subject a couple of years back, and they came, in fact, and talked to us at Cambridge, and they ran a whole article, quite a large article, about smart infrastructure. And they recognized the interest and importance of having urban infrastructure equipped with sensors using the latest technologies to actually tell us an awful lot more about how our infrastructure is performing, both in the terms of old existing infrastructure, whether they be bridges or tunnels or anything else, but also how we can actually improve hugely the process of constructing and producing our infrastructure, which is, after all, a very expensive business. And indeed, this reflects my own personal interest more in that a lot of what I do is concerned with underground infrastructure. But there is more and more the likelihood that many of our large cities of the future will be making increasing use of underground space. And this is a proposal that's being put into practice quite soon in the Tokyo station area, making much, much more radical use of underground space. But in order to do that, we need to understand much more about what we can do and how we can do it, and we need to be using some new technologies, particularly sensor technologies, to tell us that. So I'm going to give you a brief overview of several aspects of what we've been concerned with at Cambridge. The first is in terms of innovative distributed strain fiber optic sensing. Now, many of you will be familiar with fiber optic sensing using fiber Bragg gratings, where one can put specific gratings at certain points along an optical fiber to measure strain at discrete points. But there are now very exciting new developments whereby one can, by using distributed strain Brillouin techniques, by shining a light source down the optical fiber and measuring the backscattered signal, one can actually get the strain continuously all the way down the optical fiber. And one example of this recently has been an installation in a London Underground tunnel to monitor and interpret joint movements in that tunnel. And you can see here in the photograph the very the white optical fiber which has been stretched along the tunnel, and we can get the complete strain distribution all the way along that optical fiber, and that has informed in a way that's never been done before as to exactly what the mechanism of movement on this particular tunnel is. And this is a tunnel of some concern, but I should reassure you, particularly our visitors here today, that the entire London Underground system is safe, but this particular section has got some unexplained movements going on. And this use of optical fibers in a completely novel way to understand old infrastructure is a very exciting technology. And the Crossrail project, which is a huge, it's the largest civil engineering project in Europe at the moment, here in London, involving many kilometres of new tunnels and stations. And there are some very large bits of underground infrastructure. And the same process is being used. The reinforcement cage, which you can see being lowered from a crane on the top left down to depths of about 50 metres below the ground, provides a perfect vehicle for attaching optical fibre to the reinforcement cage. And on the right-hand side, you can see there's optical fibre shown both in red and in green, and it's very cheap. The actual cost of the fibre is not at all expensive, and so we can now get a completely new understanding of the forces and the strains and therefore the forces operating on these deep, expensive, buried structures. And already we are finding that these have been designed in a much too conservative way. And so there are big economies that can be made, but still ensuring that the infrastructure remains robust. MEMS sensing has also been used in a quite different way for the construction industry and for infrastructure. So there are all manner of very smart and clever technologies to do with MEMS, which many of us are familiar with. And you can see, for example, on the bottom right-hand corner, there is a strain gauge, which you'll see what looks like two tuning forks. And so if that particular device undergoes some kind of strain, then the frequency of the tuning fork changes. And this is a very accurate and extremely useful way of measuring strain, which we're now implementing on a number of examples, including the Prague Metro, where they have got quite a lot of cracks. It sounds as if I'm only showing you tunnels that are in trouble, but in Prague they do have some problems there, and these MEMS sensors have really changed the way in which the owner and operator of the metro can understand what's happening to their infrastructure. And of course, we're in a world of wireless networks, and that's changing things enormously because, again, in the context of tunnels, but it doesn't only apply to tunnels, it applies to flood defences or bridges, many other forms of our physical infrastructure, where wires leading from gauges are extremely troublesome and not at all desirable. But now we can have the principle of placing sensors of the right type into or onto our infrastructure, and they can take readings and they can beam their data to the adjacent sensor right on through to a gateway, and from that gateway to a mobile network. And so, properly designed, these can make an enormous difference to how we understand our infrastructure. And here again is the London Underground Tunnel, and what was done here was to place, you'll see there's a gateway shown there, and then a number of different devices, all wireless devices to measure cracks and inclination, placed at different places along the tunnel. And then what they can do, as I showed in the previous diagram, they can then beam their data from each device to the gateway and to the engineers. And this is enormously attractive to infrastructure owners. So there is a very big win here, because lots of our infrastructure, as I said earlier, is very old. But the question is, how is it performing? Is it good for another 10, 20, or 50 years? We can actually understand that now by using these technologies. Batteries are a problem in that they tend to have to be replaced. And so what we're also working on at Cambridge is using innovative power harvesting, such that the sensors that I've been describing will not need any batteries. And here is one particular example using parametric resonance concepts, which we've developed, where the actual vibration of the particular tunnel in question, or a bridge if there's traffic driving over it, will be sufficient to generate enough power to be stored in capacitors to be able to power the sensor. So one has the prospect very soon of having wireless sensors that will not need batteries, because they can harvest their power not only from vibrations, but possibly also from wind and for solar and other forms of energy. So, just in summary, this is obviously only a very brief description I've given you. Firstly, there are some hugely big developments on distributed strain, optical fiber systems, which are very versatile and they're widely applicable. I know of one example in Japan where highway embankments, which are thought to be rather unstable in one part of Japan, there are simply kilometers of optical fiber being used, and at very low cost, but with enormously new understanding of what those embankments are doing. Embedded MEMS sensors, they're low power and low cost and high resolution. Wireless communications, easy to install, robust networks, and finally, the prospect of power harvesting, where we can use miniature power harvesting devices and we can use low-grade energy which is available in our environment, such as vibration, wind, pressure fluctuations, and even heat. So coming back finally to that article in The Economist, they finished up by saying, the quotation you'll see on the right-hand side there, that if a car can be made smart enough to spot when the oil is low or a brake light has failed, why not do the same for bridges, tunnels, and buildings? And of course, it's not only bridges, tunnels, and buildings, as suggested by The Economist. This applies to many, if not all, aspects of our physical infrastructure. It could be critical pipelines, flood defences, nuclear power stations, potential landslides. The list is endless. And now is the time for us to engineer a smart, intelligent, more economic but resilient infrastructure. Thank you very much.